Now we're ready to work on the last scene, which is the actual production of ester. So, File, open Scene, Scenes folder, BCCE Scene 4, Fischer Collapse to Product. Should look like this. So this is the tetrahedral intermediate formed after proton transfer. And as it says in the text, it's ready to kick out water as a leaving group to form an ester. I made this scene giving you two choices. If you just want to see the animation, you can press play and click OK, and you'll see the animation that I made. If you want to make this animation, then press stop. There's this one that's grayed out, not animated, not animated. And I will show you how to make it animated, and you'll learn how to do it. If instead you want to think about what's the future of making animations like this, if you've had enough of the nitty-gritty and you want to think big picture, then maybe you just take what I've given you. To make the animation, highlight the current game object in the scene and deselect it. And instead, activate the one that's not animated, so this one on the bottom. Looks the same in the beginning, but here if you press play, nothing will happen. And highlight that, click the animation tab, and create an animation for this game object. So it'll come up with new animation. Go to Assets, Animations, and let's call this Production of Ester. Save. Okay, so now you have a blank animation to start working with. Click the gray triangle to expand. Click it again. Click it again. So that gives you the parts that are in this complicated game object. And I'm going to start with the leaving group, H2O. So one more expansion. One more expansion. Okay, so lots of children here. The H2O is here, right here in the molecule, and it needs to drift away. So if you think about the chemistry, you need to make a double bond, need to have the H2O leave, need to rearrange the geometry to sp2. So we'll do those three things. I'm going to start with the leaving group. So highlight H2O. On the animation window, 50 frames has been our standard. And the H2O should drift away. So to do that, click the record button. Go up to the right and do transform. This is just guess and check. Make it look good. So I'm going to try x equals -2. Y. This is kind of backwards than what you would expect. But I'll try y equals 3, y equals 4. That's reasonable. It's drifting away. We'll give it some more rotation. So maybe 60 on the Y, 40 on the Z, 10 on the X. And this bond that you see I'm pointing at, that needs to go away. The formal negative needs to go away. I think the bond should go away faster. So it is this bond to carbon. Highlight that. I'm setting mine to 20 frames because it looks funny to have it coming out with a bond. So the bond should shrink away. Expand the bond to carbon and find bond stick. Highlight that. Y scale 0.2. Y position 0 will make it disappear. I'll have the formal positive charge also disappear on the same time scale, so it goes away pretty fast. Highlight formal charge marker. Timeline is on 20. Scale on the transform 0, 0, 0. Let's take a look at that by dragging the timeline marker. So it's popping out, moving away, doing a little rotation. So I think the water should keep moving away after that 50 frames. So we'll set the timeline to 150 frames and go from there. Okay, 150 frames. Where should the water be at 150 frames? So I'm highlighting H2O. Here I experimented with different parameters. For position, ended up with x -5, y equals 8, rotation, x equals 30, y 200, and z equals 90. Looks decent. Okay, so now if you scrub through from the beginning, let's see what happens. In the beginning, it's bonded, drifts away, continues drifting away, and it's clearly independent of the original molecule. All right, that's fine for the leaving group. We're ready to move on to what happens with the carbon here that's going to become sp2. So now I'm focusing on the bonds to the carbon. So we've already got the water, it's going to leave, and you can see this exposes the bonds. Going to make this into a trigonal planar geometry and make a double bond here between carbon and oxygen. So let's start with the bond to hydrogen. That's the one in the back. Set the timeline marker to 50. And you can see the water's out of the way, so it allows you to see what's going on. Record button is on. Bond to hydrogen in the back. Going to bring it forward and make it the right geometry. So that means Y goes to 0. That brings it into the plane. And Z should go to 60. Yeah, so this is now a 120-degree bond angle between this HCO. And need to do the same on the right. That's labeled double bond to oxygen. So here, all we have to do, I think, is make Z equals 60. You can see Z equals 0 straight up. Z equals 60 will bring it to the right. And then this is now 120-degree bond angles. Looks good. Let's see what it looks like. Okay, yeah, kind of cool. Yeah. Rearrange the bond angles as that leaves. And now make the double bond form right here between carbon and oxygen. So that you'll need to expand double bond to oxygen. Should see 2 bond sticks. Only one is visible right now. That's the first one. And the one that says bond stick parentheses 1 is invisible. So let's make it visible. It's inside the oxygen right now, so let's bring it out. Make the Y scale 0.5. So make sure you're on 50 frames. Record button. Y scale 0.5 and Y position 0.75. Okay, so it looks like you can't see that it's double bond. So let's move the first bond stick over. Highlight bond stick and set X position to be 0.1. Maybe that's all we need. You can see the double bond forming, huh? That's pretty nice. Okay, and then the formal positive should appear on this oxygen. Okay, a couple more details. You can see the hydrogen should go into the plane of everything else because it's going to be sp2 oxygen. Time marker on 50. Record button set. Highlight oxygen. This is the atom and set the Y rotation to be negative 60. That'll bring it coplanar. And the formal positive should appear on the same time scale, so highlight that. And set the scale to be 0.12, 0.12, 0.12. Let's take a look at that. So lots going on. Leaving group is leaving. Double bond is forming. Bond angles are changing. That's beautiful. So to have this proton come off is kind of tricky. So I'm going to try this strategy. It may not be the best, but it'll be a reasonable illusion of what's happening. So I'm setting the timeline marker at 110. Record button is on. So first I'm going to expand the oxygen atom. That's a child of the double bond to oxygen. And highlight this bond stick. All right, that's this bond between the oxygen and the hydrogen. Need to animate three things here to make an illusion of this proton coming off. Bond stick highlighted. Timeline sent to 90 frames. 90 frames. Okay, 90 frames. Go up to the transform and just retype the position 0.75. You can see it's turned red. It's recorded this now at 90 frames. And Y scale 0.5. Then after that point, it's going to shrink away. So drag your timeline marker to 120 frames. Set Y position of this bond to be 0. And Y scale of the bond 0.2. You can see in those 30 frames it shrinks away, leaving this hydrogen all alone, so that's going to become an H plus ion. To do that, highlight hydrogen atom 1, timeline on 110 frames, and simply uncheck the box at the top so the hydrogen atom disappears. Then highlight H plus ion, and we're going to make it appear at that moment. So 110 frames. So it'll be an illusion that the hydrogen atom turned into an ion as the bond shrank away. Okay, for this H plus ion, we want it to drift, which means you need to set its starting position. So just go to Y position and retype what's already there. And then we can drag the timeline out to 180 frames. You have some leeway here. It could be more, it could be less. And have it drift out to the right. So I'm going to try x equals 6. Y equals 1. That's probably fine. Take a look at what it looks like. Okay, double bond is forming. Bond is shrinking here. So it happens pretty quickly, doesn't it? And then H plus is born and it drifts away. Okay, last thing to do is take care of that formal positive. So I think it should start shrinking away from 90 to 110 frames so that the positive charge is carried away by the proton. So let's see, where is that? That's right here. Formal pause marker. Timeline's at 90. It already has an animation, so let's just do this. Retype its current scale, 0.12. It makes a key frame at 90. And then by the time 110 frames happens. So I've dragged it out to 110. This positive is now in the proton. So I'm going to do the X scale of the formal positive 0, Y scale 0. And you see it's gone. That should be it. Before you try this out, click the record button so it's no longer recording. Click the animator tab. Should see an orange box. Your name will probably be different than mine, but that doesn't matter. So click that orange box once. Set the speed to something slower than 1. I recommend 0.25. And then double click the orange box and take off the loop. Okay, that should be ready to go. I would save your scene. Control S will save. Press play. And enjoy what you've built. So there's the ester right in the middle. The catalyst is regenerated. Water is a product. That's the Fischer Esterification. So at this point, I encourage you to talk to your neighbors, talk to your presenter, Steve Sogo, and see what you think about whether this has a place in your curriculum. Clearly, there's an opportunity here to learn as much as you like, to be as creative as you like, and I can help you do that. So that's my role here at BCCE and beyond, to help you become a creator.